In this video I'm going to be going through exercise 1.2 on page 16 of Engineering Studies, the Definitive Guide Volume 2, second edition I think. So it's not the most recent, so page numbers could be different. In that question what you have to do is find these two reactions, reaction left and reaction right. I'm not going through that, I'm going to say that the book already does that. What we're going to do instead is we're going to solve all of the members in this truss. So what we've done is we've broken the 250 kilonewton force into the vertical and horizontal components. Why we did that is because I'm using the Johns Hopkins truss analysis software. It's probably going to be the thumbnail for this video. And I use that to compare my results. When I put this on Google Classroom, we'll probably have a screenshot of that as well. It's good because I've now realized that with Johns Hopkins, since they updated it maybe a year ago, you can actually get pretty exact measurements and you can get pretty exact forces and you can actually scale the forces. And this is how you should be doing your designs for your trusses. Speaking of which, can you see that makes its way home? Okay, now I also labeled this. You have to have labels really to refer to things. So I've left and right. This point here is left and this point right. You'll notice I've drawn the green arrows. Often I tend to draw the green arrow below the reactions. This time around I actually drew the green arrow pointing actually to the dot because that's where they're applying the force. Otherwise sometimes it looks like it's applying the force slightly above or slightly below. So like here, this arrow is actually in line with P. I've written it a little bit below just so that you can see. Right? So I'm just explaining that this is a little bit below. It's actually really, in reality, it's in line with that force. Yeah? Okay. Now, I've left L and R. They were already labelled for me. I've then gone with K, P, and Q. I've just chosen those letters because they're sort of between L and R in the alphabet, and I jumped over some ones that can be a bit confusing, like O is not a good choice to use. Okay, so now that we've gone through that, we're going to start by finding the letter K. Now when we're going to find the letter K, what we're going to do is we're going to put a section. We're going to solve all of this using the method of sections, and we set a section line somewhere that goes through the letter K. Now I've said we could go through the letter K here. We could also go through the letter K here, right? So we can do different cuts, and we can see I've drawn those cuts up here, right? It's a little bit crowded now, so I'm going to draw it again in the space down the bottom. But if I cut here, right, through from KQ to LP, I'm going to get something that looks like this. Right? That's what my cut will look like. And my external forces are this force and this force. They're my external forces. And then just everything else, I just assume tension. Right? So I write assume tension, assume tension, assume tension. Right? That's one option. That's what I've drawn up there. Yeah. Now, the alternative is that I can cut this way. And if I cut this way and just take the left-hand side, I get this diagram. And we're going to compare, would I be better off cutting the left or cutting the right? Yeah? Now I could actually have cut this way, and I can actually compare that to this. It's not the world's best drawing. I could use the left-hand side and the right-hand side. And sometimes for homework, what I make people do is I say, I want you to solve it, but this time from the right-hand side. Because the thing is, these values, the left and the right, the left and the up, they should be exactly the same. It doesn't matter which way you approach it, they should be exactly the same. Now, the point is, I could cut here, I could cut here. It doesn't really matter where I cut, because as long as I cut through KQ and I only have two unknowns, I'm happy. It doesn't matter to me if that unknown is KP or PQ. Sorry. It doesn't matter to me if that unknown is KP or PQ. It doesn't matter, right? It doesn't matter which unknown it is. In this situation, I have two unknowns. In this situation, I have two unknowns. In that situation, I have two unknowns. So that's fine. Okay, so now that we've drawn up that, the downside of that is that it does have more forces. There's more forces if we take the left-hand side than if we take the right-hand side. So that's where we'll come back to that as we go. Now, I've already written up this first one because I started doing it with my class, and we're going to we'll keep going from there. So what we've done is we've said, if we're looking at this, well, I wish I hadn't rubbed out that now. If we're looking at this first this first section that we've taken, we have KQ as our target. Good hand in, well, the reasonable hand in poker. KQ is what we're looking for. And we have two distractors, KP and LP. How do we eliminate them from, and what method do we use? Do we use Meetup or Lone Wolf? Meetup. Okay, KP and LP, they meet up at P. So we're going to use the Meetup method. And what formula do we use for the Meetup method? Do we use moments or forces? For Meetup we use moments. For Lone Wolf we use forces. Yeah, so that's my mnemonic. It's not a great mnemonic, that's what we're going to use. Okay, so what we've got here is this convention means that we're using clockwise as positive. That's what this convention means. We've used sigma for sum of all the moments from measured from point at P, we've said P, equals 0. So the sum of the moments about P equals 0. Now, let's look at all the forces. We have lots of forces in this diagram, right? A lot more than we normally choose to use. So here we have, touching P, we have KP, LP, so that's 2, 3, 4, 5, 6, 7. I've got 7 forces. Let's have a look. 1, 2, 3, 4, 5, 6, 7. Okay. Now I already did this before, but I had this decimal place moved out because I had it to the wrong scale. And it took me a long time to figure out what was wrong, and I tried to look and say, well, have I left out a force? And that was the first thing I did to try and figure out what I'd done wrong. Okay, so KP and LP, why have they been crossed out? KP and LP, why have I put a cross through them?
Is it 0?
Yeah, because anything multiplied by 0 is 0. It doesn't matter if it's 2 multiplied by 0 is 0, 2. If I have 2 groups of nothing, I still have nothing. If I have a billion groups of nothing, I've got nothing. So the fact is, it doesn't matter what these two unknowns are. The reason why we use the method of, the reason why we use moments is because if we multiply by a location, we can eliminate unknowns. That's what we do with our reactions, and that's what we do with our method of sections. Okay, so they might both pass through, so they're 0. What about this 216.5? How do we get rid of that? Because it runs that straight line. Now, I said right at the start, I drew that force running down below. But in actual fact, that force is running through this line of P. Yeah? It's actually applying the same line as the dot P. So because of that, it means there's no perpendicular distance. If there's no perpendicular distance, we multiply by 0. We don't even need to include that in our calculation. And most people won't. I include it in the calculation because I want you to understand where these forces are disappearing to. But sometimes you'll look at HSE answers, they just won't include that. It's a common, more often than not. Okay, so let's have a look at our next force. Our next force is 56.3, and how many triangles away is it? From P, measuring from P, there's a green dimension line that shows it. From P, how far away is this force? 1 triangle away. Now, previously we talked about 1 t's worth of triangles, but we're not going to do that. We did that once and once only. After that, we're just going to say 1 because we don't want to have to reduce. Like those t's will cancel out, so we're just going to ignore it. We're just going to say 1. Okay, so it's 1 triangle away. Now, is it going clockwise or anti-clockwise? If I put my finger on P and I spin the clock, right? So if I have my clock arm, right? Is that 53, is it pushing the clock arm clockwise or anti-clockwise? Is that 53, is it pushing clockwise or is it pushing anti-clockwise? It's pushing it that way, which is?
Clockwise.
Like a clock, okay. So, the other way I like to do the Wheel of Fortune, clockwise. Okay, what about 61.5? Which way is it going? Clockwise or anti-clockwise?
Clockwise.
Okay, so that's going clockwise. So I always write it as a negative, and then I change the symbol when we get to it. Okay. So that's 0. How far away is it from P? What's its distance from P? What's that distance from P? So, you see how I'm drawing it as like a parallel line? And I'm saying at what point is it closest to P? It's closest there, right? Yeah, if I extend that line forever, where is it perpendicular to P? There. What is the distance of that line? How many triangles? It's shown on green. Someone?
0.866.
Thank you, 0.866. Okay, we've used 0.7. The reason we use 0.7 is because that is the accuracy to the scale that I've drawn on the Johns Hopkins Trace Analyzer. Okay, the next is 125.5. Is it going clockwise or anti-clockwise? So again, we're pushing down, and we just keep going down until it reaches the perpendicular line, and then we're going to... Which way is that going? Clockwise or anti-clockwise? So we're going to leave that. We're not going to change that from a negative. Okay, how many triangles away is it from P? Now you might look at that and say, it's way up here, you know, but no, we can imagine, we extend that line down, right? We extend that right line down until it's how many triangles away?
0.5.
0.5, thank you very much. Okay, so 0.5, and then lastly we have KQ, right? So how far away is it? How far away is KQ? What is the perpendicular distance? So in this case, we can actually draw, that's our force. If we drew this up, we could say, well, what is that distance? What is that perpendicular distance?
0.87.
Thank you very much, 0.87, okay. So, why is it positive? Ready? Clockwise or anti-clockwise?
Clockwise.
Clockwise. Okay, it's clockwise, but how did we know that? There's no arrow on the diagram, there's no arrow here. Why did we draw the arrow going in that direction? Because we always assume what? Yeah, we draw everything, we draw the pulling from the node, right? Pulling out from the node, which we assume is in tension. Right? If it's in tension, the force is pulling from the node. If it's pulling from the node, it's going clockwise. Which is why I've written here, assume tension, therefore clockwise. Yeah, and that's why it's positive. Okay, next, what I need to do is I need to type in this calculation. So this I left rubbed out because I had to redo it. Plus 0.83 minus 62. Let's hit the calculator. Someone should have an answer for me there. So we've got 56.3 plus 188 minus 62.5 equals 181. Okay. Yep.
There might be a mistake.
Go ahead.
Me and Sir both got a different number for the, instead of 188.1, got 193.
193? Okay, I might have typed in the wrong thing, sorry. Thank you, excellent. Okay, so it's 216.5 times 0.87. 216.5 times 0.87. I get 0.88.
Okay. Never mind.
No, just well, everyone do one check. Yeah, so 216.5 times 0.87 equals 0.88. Yeah?
Okay, yeah, sorry.
Oh good, oh good. Much rather people tell me that, okay, so what I'm then going to do, oh, this number is wrong. What I'm going to do is, I've got 181.8 divided by 0.866 equals 209.9, which we can see their answer is 208.8. Pretty close, that's good enough for me, right? So I've got 209.9. Why is it different? There's, they're using just slightly different numbers. That we're rounding to the nearest tenth, they're using the numbers to the nearest hundredth, is probably the reason. Otherwise I've tried to keep, and obviously this, I tried to keep it as close as possible, but yeah, anyway, more than happy with that number. Before I was getting a number that was way off. Okay, so you can see here I get the same value when I do it down here, but let's go through that. If we take this side, what are we going to do now? So where is the meetup method going to, where are we going to meet up in this case? Where are our unknowns? Our target is KQ. We have PQ and PR. We need to eliminate them. How do we eliminate them? Meet up. Where are they going to meet up? At P. So we're going to take the positive clockwise sum of the moments about P equals 0. 0 equals, let's go through our forces. Now in this case, you notice that I didn't write the zeros. Yeah, I didn't write PQ and PR because they're just multiplied by 0. I don't have a diagonal, I don't have a horizontal force acting in this line, so I can ignore that. So I then have KQ, oh sorry, I start here. I said measuring from P, I have this force, 294, one triangle away. Is it going clockwise or anti-clockwise? Anti, so minus, we keep it as negative. I have this force, 255, it's half a triangle away. Yep? Which way? So it's positive. What about KQ? Clockwise or anti-clockwise? Now, I didn't really drive that home before. So again, we assume tension. So I've written negative. So what I'm going to write here is I'm going to say assume tension, therefore anti-clockwise. Now you notice in this diagram, tension meant clockwise. In this diagram, tension means anti-clockwise. It's all relative to your reference point. Yep? Okay. So then we get an answer that is negative. So I write here, now you don't need to write this. I'm writing it in blue to let you know that it's not something you need to write in. So I said negative, therefore my assumption is no good, therefore it must be not tension, therefore compression. Right? Then I take the sum, I calculate 175 divided by 0.866. And that gives me 209 kilonewtons compression. Now, for my other class, who had to sit through me scratching my head trying to figure out where the error was, this decimal point here, what I did is I knew that I had my trace analysis software. So I was trying to see, is that where the fault is? And I tried to reproduce it in another software. Unfortunately, I couldn't get other software to work. I went through the effort of modeling it in, there's another program which I have used before, but only once or twice. I'm just going to give it a shout out, called SkySieve. I set it up, and you can see, my class will be able to see that. I did actually draw it in SkySieve, but when I tried to solve it, it told me that I couldn't use it in my school network. So the other ones that I just, when I hit, they all seem to be blocked by the school connection as well. I have used this one, Valdiviva, but that one just wouldn't even open in school. The thing is though, so what I did is I just ran another one. I did another one which I already had the answers for. And when I ran the other one that I had the answers for, I'm like, yes, I can definitely confirm that it's not just like that John Hopkins' website is suddenly broken. Or at least I felt more comfortable about it. But by taking moments from another section, by going from the other direction, I was able to say, well, this number here is different to that number there, and this one matches the one on the diagram, so that means there must be something wrong in my working out. And then I was able to go through just force by force, and eventually I found that, okay, it's actually, I looked back at the diagram and realized I was using 50 on this diagram and 5 on that one, and there was a mismatch. Now, in terms of HSC process, it's worth noting that if it's just simply a matter of you carried the wrong number across, if you wrote down 90 kilonewtons instead of, or 90 newtons instead of 60 newtons, and you just wrote down the wrong number, they'll probably give you the full marks. The marker will be a little upset because they'll have to take the calculator out and just check, okay, where is the error here? But there's a good chance, especially for, I can tell you that I've spoken to senior markers and I have a very good understanding of like 6-mark trust questions. They're not answered very well, so it's really a chance to gain some advantage over the rest of the cohort. Okay, so now that we've solved KQ, now what we're going to do is we're going to start actually labeling this diagram here. We're going to label the internal forces. Now this is not something that we need to worry too much about. When I was a student, this used to be a huge part of what I did, was labeling these diagrams. These days not really a thing. Now for Johns Hopkins, you can see that they have red for compression and T for tension, right? That's what they have. Red for compression and T for tension. But what we're going to do is, instead of using colours, mostly because I don't have a red texture, instead we're going to use arrows. Now, what I'm going to do is I'm going to say, well, because we found that this was in compression, remember we assumed it was going in, we're going to reverse that. Right? We're going to reverse that because we now know better. Our assumptions were wrong, we now know better. So we're going to draw an arrow going into the node and into the node. Now I have a song that I'll play when I'm not recording about how I remember this. But I'm going to say that symbol, that's the symbol for compression. If you see that labelled on a diagram, that would be the symbol for compression. I like to think it looks a bit like a C, especially if you join up. Looks a bit like a C. Anyway, if that helps you to remember. Anyway, so what we're going to do is we're going to label that, and we're going to say that that is 209. We're just going to call it 209 and split the difference. Even though I get 209.9, I'm going to trust the software here that says 208. Definitely close enough that we're not getting anything marked down. Okay. So we don't need to write compression, the arrows tell us that it's compression. Okay, so the next one we're going to do, well, I'm going to let people pick. We can either, I've already done in my other class, I did KP to see what my error was. And things I knew I was still getting the error because I cut on the other, I took the left hand side again. Okay, but do I want to go with KP or LP? My wife's initials and my initials. KP or LP? LP, great. Okay, so we're going to go with another, we'll have a look at that one. Has everyone got the left-hand side of the board? The right-hand side of the board? Yep, okay, I'm going to clear that. Ready? Let's build it up from scratch. Oh, as a matter of fact, can I ask you to turn on the light, please? I should have done that earlier. It really does make an effect on recording quality. Yep, all of them. Can you close the door too? Okay. So first thing we're going to do for LP is we're going to have to cut somewhere. Where do we want to cut? We could cut here. That would work. Or we could cut here. I'm going to show two different ways of cutting this. Right? I'm going to show this cut and this cut. Yeah. Okay. Let's see how different that is. What we saw last time, I'll just point out, is that there's a lot more stuff going on in the left-hand side, which I'm going to say makes it more difficult than when we use the right-hand side. So what I'm going to try and do is, for the moment, I want to try and have the least amount of truss possible, as a general rule. So if I go there, that's not very much truss. But if I go this way, that's the least amount of truss I can have on the right-hand side. So I'm going to do those two different cuts, and I'm going to compare them. So this way looks like this. We have, again, I'm going to show these forces not as the diagram. Okay, I had an interruption because I drew the wrong diagram, but we've fixed that now. So, what we need to do is we need to find the location where, somewhere on the point LK, somewhere that LK passes through, that's not L, where we can take our moments about. We can't take L, because if we take L, everything else passes through L, so it will all be multiplied by 0. So the only other location we can use is K. So what we're going to do is we're going to say sum of the moments about K equals 0. So sigma moments measured from K equals 0. And we're going to say 0 equals, well obviously LK multiplied by 0 is nothing. And then we're going to say LP. LP is going anti-clockwise, so I'm not going to change that. How far away is it? It's 0.87 triangles away. We then have 216. 216 is going clockwise. So, and it is also 0.87 triangles away. Then I have 53, which is also going clockwise, right? Right? 56.3, and it is half a triangle away. Okay, we got it all on one line, which is pretty rare. You don't need to write this. The LP is negative because we made an assumption that it's in tension. If we assume tension, it will be anti-clockwise. That's why we got negative. Okay, I find actually drawing the little arrow does really help. Okay, so what I've got is minus LP, so I'm just going to bring that straight over to the other side. I'm just going to add LP to both sides, so I get 0.87 LP equals this number plus this number. Thank you, 216.5. 216.5. LP is going to equal 216.5 divided by 0.87, or sine 60. Now, that number will have to be bigger than that, which is? 248.1. Now, our answer was positive. Our answer was positive. So, therefore, it is in tension, right? Our assumption was okay, therefore it's tension. So we can just write, this is close enough that we're just going to call it that, and we'll say newtons, and we're going to say tension. Now, I can see on the board that that is the same answer that they had. What we're going to do now is we're going to pick a totally different way of solving this and see that we get the same answer. So what we're going to do now is, like I said before I stopped recording, is we're going to cut here and take all of that side. We're going to take this side. We want to go from the left, and what we're going to take is we want to take as the smallest amount of left that still cuts through LP as possible. So that's what we want to do. We want to try and simplify our thing down as much as possible. Okay. Now we like this because it doesn't have any diagonals. 294 newtons. 225. So only two external forces, that's good. Right, it does cut through KQ. And it cuts through KP. And then we have LP. We're looking for LP, so what location are we going to take moments about? Okay, let's take a step back. We have KQ and KP. So our target is LP, our distractors are KQ and KP. What are we going to do? Do KQ and KP meet?
K.
At K. So if they meet, we're going to use the Meetup Method. Yep. Okay, so I'm going to say clockwise is positive. Sum of the moments measured from K equals 0. 0 equals. Okay, how many forces have we got here? We've got KQ, KP. Do we need to write those both down? No, we're not going to do that anymore. We've done it already a couple of times in this video. We're just going to say we don't need it. We're just going to know that they're 0 because they've been eliminated. So we've got 3 other forces. 1, 2, 3. We'll go clockwise. So we've got minus 2, 2, 5. Right? Now, I've written minus because it's easier to turn a minus into a plus, but then I'm going to put my finger on K and I'm going to spin the wheel. That is a positive, that's clockwise. Okay, what is the distance? It is 1 triangle away. Then I've got 294, I'm going to spin the wheel. Anti-clockwise, it stays as negative. 294 brackets 1.5, and then I have LP. LP, thanks Siri, I have LP, let's spin that, right, K on, now why is this arrow the way, why did I draw that arrow that direction? When I did this cut, how did I choose where these arrows were leaving? We assumed tension. Right, so I put my finger on K, I spin it LP, clockwise, so I'm going to write plus LP brackets. Now how many triangles away is it from, what is the distance from here to here?
0.87.
Right, that's exactly right, thank you. And this distance here is 1.5 triangles. just to help make that a little bit clearer. Okay, so 0.87, it's actually 0.866, but just when we're using Johns Hopkins, we're going to use 0.87 just this once. Okay, so we're going to move this LP over here. We're going to say minus 0.87 LP equals, I don't suppose you've done that for me already. It's going to be a negative number, I think.
Negative 216.
Nah. I think that's, maybe.
Because it's times 1.5.
Yeah, times 1.5. Yeah, okay. Usually I'm pretty good with my estimation, but $216. Okay. Thank you. They cancel out. So it's tension. Now, given that I literally did this question a few seconds ago up here, they do need to be the same, like I said earlier. Okay, so what I'm going to say is LP equals 216 divided by 0.87 equals
248.4.
that's the same answer we got above. Okay, which one is better? Which one's easier? For me, they're both pretty good. They're both pretty reasonable. I would be happy to use either of those two solutions in this particular case. Okay.